Okay, is it working now? Can I just keep it on there? If you're gonna keep going, camera, I'm gonna come check on you in a minute. And if you stop, oh my goodness, she better come by and do my RAM today too. All right, listen up. We're going over the check-in. Are you ready? Camera, are you still recording? I will get you. Okay, it's still recording. There you go. Thanks everybody for your patience. Okay, well, the cork from a sparkling grape juice bottle, yeah, is launched straight up with a kinetic energy of 5 joules. It has a mass of something. How high? It looks like this is going to be a math question, so I'm going to write down this energy it gave me. However, if you know about these energy problems, it usually is like, okay, well, what energy did it come from, or what kind of energy is it going to go to? And it's not going to be kinetic energy. So when it gives me energy, I like to write down just that it's going to be some kind of energy that I don't know what it is, and that it gave me 5 joules. Bing. Okay, it has a mass of 0.05 kilograms. Camera, are you still recording? It crashed on me earlier. That's why my video was late today. Okay, good. Oh, how high will it go? Asking for H for height. Hey, where do they have grapes? Where do they grow grapes?
Greece.
Greece? Where's Greece?
Italy.
Well, Greece and Italy are two separate places. Where are both Greece and Italy located?
Mediterranean.
Where is the Mediterranean area located?
Europe.
Where is Europe located?
On Earth!
Earth!
Too many questions.
The Milky Way. So that's another thing we know. And I'm writing this down. Bg's equals negative 9.81. Because, is that an 8? Because it asks for H. The only energy formula that has a H that we can use to find H then is this one with the MGH. And now we have the G's. Thank you for figuring out where the grapes were this night. Well, they're on Earth. So let's figure out how high it went. So our energy, see what had happened was, this marker had a kinetic energy, and it all got converted into potential energy, like this. I'm going to give it kinetic energy, and it's going to convert it to potential energy. Kinetic, potential, up there. So I think it may have left the frame for a minute. I'm sorry. So it had so many joules down here of kinetic energy, and then up here it had 0 joules of kinetic energy because it stopped. It converted it all to potential. So that 5 joules turned all into potential energy. Its mass was 0.05 keys. It was on Earth, because that's where they have grades. And H is what we're looking for. So I'm going to simplify this to joules. And then we got to do 0.05 times negative 9.1. I did this earlier. It's 0.4905. H is still there. If you notice, this 0.4905 is actually in newtons because it's kilograms times meters per second squared, which is mass times acceleration. It's just the acceleration due to gravity. Wow, that doesn't actually matter, but just so you know, we're going to be using newtons, so you will need to know that that's what newtons are. It says all this times H. I want it to say equals H so I can get my answer and be done so we can do the lab. So since it says H times negative 0.4905, I'm going to divide both sides by negative 0.4905. 5 divided by negative 0.4905 makes negative 10.2 meters. It's negative because remember in this formula, it has that potential energy because it has the potential to fall down that distance. And that's what the negative is for, to stay down. Thank you, Cole. It asked how high will it go, so it'll probably make more sense for us to say it went 10.2 meters high instead of negative 10.2 meters. I'm just letting you know why it gave you a negative when you calculated it. You can say it went 10.2 high because it wouldn't make sense to say it went negative 10.2 high. Not as much sense. Cool? All right. All right, well, if my camera is still recording. Camera? Still recording? Okay, camera's still recording. I'm going to talk about the lab. There we go. Watching you, camera. The lab. Lab, fine. Can you see? Camera, can you see? Okay, there. Well, we're doing a lab. Your instructions say to find an object that you can balance, which is what we're using as a meter. Our meter sticker is using for that. This is our balanced object because balanced it. It wants you to find 2 known masses. If you want to have more than 2 known masses, that's okay, but the table only has a spot for 2 known masses, and it's going to make it easier for you to do both tables if you use the same 2 known masses each time. So I actually used a little scale to mass these. These are the alternate mass holders. If you have something that looks like this at your station, that's an alternate mass holder. The long rings are over by Gabriel, and the short rings are over by Liz, and the hook stands are over by Jessica. Everybody else has a little hanger that doesn't look like any of these. That has a little hanger and a little place to put the little masses on it that you have. Those have the mass stamped on them, so you'll be able to figure it out there. When you're adding up the masses, I recommend you add them up in grams because grams are stamped on there, and then convert to kilograms later. By, if you get 100 something grams, 110 grams, that's 0.11 kilograms. So you're moving the decimal 3 places because there's 1,000 grams in a kilogram. So these are 110 grams. I'm going to load this one up and make it twice as much. I'm putting a 100 on and a 10 on, so now this whole thing is 220, and this is 110. What we're doing, that's a little confusing. We're not doing circuits anymore, are we? What we're doing here is we got to make this balance. I'm going to put this one 20 centimeters away from the middle here, from the fulcrum, or balancing point, or axis of rotation, as we're calling it. Torque here, as I mentioned in that one check-in, is like force, but it's in a circle. If I let this torque spin this thing, it's spinning like a propeller in a circle. So if I put this one that's twice as heavy, twice as massive, over here on this 20 centimeters away, how far away should I put this other one?
20 centimeters away.
Huh?
Twice as far as well.
Twice as far, yeah. This is twice as much mass. To have this one have the same torque applied as this one, and it's only half as much, it has to have twice the distance, and then our torque will match. Let's see, so that's 40, that's 20. This should work, right? Hey, it worked! And just to prove that I don't have this thing screwed in, make sure this thing can balance freely. If you take one off, it should fall like that. But, here, I'll put it back. When you do this, it'll want you to write down the distance from the center of the thing. Okay. So you'll have to add up your masses. So I've got 110 grams, which is 0.11 kilograms. 220 grams, which is 0.22 kilograms. And that'll be my mass. So 0.11, 0.22. The weight, it tells you in your thing, you've got to calculate the weight. Bless you. It's F equals MA, where A is negative 9.81 because weight is caused by gravity. So I'll say 0.11 times negative 9.81, and that's my weight there. 0.22 times negative 9.81, that's my weight there. They'll be negative because these are pushing down on this miter stick. Force is exactly the same as weight. I just wanted to remind you that weight and force, the weight is a force. And force is like weight is a type of force. For position from point of rotation, that's how far they are from the middle. make sure you do this in meters. So like this one is 40 centimeters. This one is on the 10 over here, but don't put 10. You're measuring how far it is from the middle. So it's 40 centimeters, which is 0.4 meters. This one's 20 centimeters from the middle, and that's 0.2 meters. So I'll put, I don't know which one's which, 0.2 meters, 0.4 meters. And then torque, you may notice it's in Newton meters. Can you see it? Newton meters. That's the force here times the distance it is from the center. So that's why this one's that's twice as much with half the distance has an equal torque to this one that's half as much weight but twice the distance. Right? Did I say that right? This one has twice as much weight, half the distance. This one has twice as much distance and half the weight. You'll need to make 2 tables. One is for the first one you did. You got both your masses here. You'll fill out your table according to your first balancing thing. And then you move them. So like if I move these somewhere else where they'll balance, where can I put this? Yeah? Okay. Then I can make a new table like this. If you'd like to make more weights, you can, but then your first 2 columns here and here, I guess first 3 columns, would be different if you added more weight to it, but you can. And you can just make a new table with all new numbers. But if you just move these, like I just did, then these 3 columns would be the same, and you're just changing this and this. Sound good? Please don't mix up the things at the stations. Keep the stations exactly where they are in the part of the table where they're at, so that they can stay, distanced from each other. Man, I don't want to put these away, but it's going to be Wednesday before the other students do. Anyway, please go try it out. Try not to run out of time. Oh, my camera's still going. That's good.